Good morning, ladies and gentlemen. On behalf of Team Acumentrics, I'd like to welcome you to the Fall Symposium. My name is Michael Mashalani, and I'm working alongside John Travlin, Nate Mensa, Jeremy Peacock, and John King, with the help of our technical directors, Brendan Smirbeck and Peter Upchek, and we've been tasked with designing and building a network-managed power distribution unit. Now, some of you may be wondering what a power distribution unit is. You may have seen them in a simpler form under your desk distributing power as a power strip. The difference is a power distribution unit delivers higher power and has extra features such as fault protection. Now, most Capstone teams will speak about what they've been given and what they do with what they've been given. But in our case, we weren't given much. We were told simply to make a smart PDU, and we were given the freedom to make our own decisions, hardware and software. Having no previous power electronics experience, we started with researching simple power distribution circuits in power strips. We found that the main component in a power strip consisted of 3 bus bars carrying hot, ground, and neutral, and we used the same concept to draft a schematic and build a fully hardware prototype. This full hardware prototype consisted of 3 bus bars for hot, ground, and neutral, high powered, pegboard as the base, and 14-gauge wire to carry power safely through the system. After having a full hardware prototype, we needed to think about the smart features. These smart features consisted of multiple sensors, a relay, and a microcontroller. The sensors are used to monitor data throughout the system in case something goes wrong. The relay is used for remote toggling in case the user can't get to the system physically, and the microcontroller is used to hold the software.
Now that we decided what features we'd like to add to our system, it came time to select components that were able to perform these features. The first of which is an 8-port power relay module. This 8-port power relay module is able to toggle each outlet on and off. The next component is a temperature and humidity sensor. Now this temperature and humidity sensor is able to send data to the microcontroller, and this data is able to read the temperature and humidity of the system. Now the next sensor that we needed to implement was a current sensor. This current sensor is crucial to our design. Now, initially, our technical directors suggested that we use an isolated differential amplifier along with a shunt resistor. And having no prior knowledge of using this, we performed research on how to implement and how to design our system with this. And in our research for the design, we were able to find a Hall effect sensor. And with this Hall effect sensor, it is also very accurate and is able to feature an isolation barrier. Now this isolation barrier is able to separate 120 volt AC and the low voltage for the microcontroller reading. And this microcontroller reading is able to receive the 5 volts to collect the data. Now the next is voltage sensing. For voltage sensing, we use a simple voltage divider circuit. And for the voltage divider, it is done by this passive element. Now this passive element required that we step down the 120 volt AC to 12.9 volt AC, and later rectified that to DC using a bridge rectifier. And that DC voltage was able to give us a steady voltage for a more accurate reading.
Now that our sensors have been decided, we needed a microcontroller in order to read them. Our temperature sensor sent out a digital signal that could be read through our microcontroller. However, a voltage and current sensor sent out analog signal that couldn't. As a result, we needed an ADC or analog to digital converter in order to read those values. Our ADC that we uses a reference voltage in order to get its values. Because of this, we had to make a conversion factor in order to accurately get our current and voltage values. Our final hardware decision was choosing a microcontroller, which we decided on the Raspberry Pi. It's low cost, efficient, and was perfect for our situation compared to Arduino. It also allowed us to have a dynamic start to our software development process. Now that our hardware design is complete, we're now ready to start schematic for PCB fabrication.
Now that we had smart hardware, we needed to build a software system to accompany this hardware. Because of the freedom we were given, we opted for developing a web application. Despite having no prior experience with web development, We chose web application because it is cross-platform. We build one application regardless of the operating system. This severely reduced our development time. Also, web applications run in the browser, meaning no installation is required, removing hassle for the user. To structure our system, over on the server side, we utilized a software bundle called the LAMP stack, which uses Linux for the operating system, Apache for the web server, MySQL for the database, and PHP for the server-side language. The reason we use the LAMP stack is because we are using a microcontroller. We needed a software bundle that gave us performance on our specific hardware, and we found the LAMP stack gave us this performance. Over on the client side, we started development on a graphical user interface, or GUI. When developing this, we kept in mind ease of use and intuitiveness. Shown here is our main page, the system overview, which we designed to give the most pertinent information to the viewer, such as the on-off states of the applets, as well as the power currently being drawn from each applet. The user is also able to see any metric they wanted on a real-time line chart. To reduce clutter on the page, we opted for only having one line chart instead of a chart for each individual metric, and we allow the user to select which metrics they would like to view on the line chart. Also, due to different applications such as routine observation or perhaps testing, we allow the user to select what time frame they want on the chart. Along with observation, we allow the user to control the system via buttons under the outlets that toggle the relays associated with that outlet. This page contains the tools to allow the user to monitor and control the system, which is the main motivation for the project, all right here. Now, if something unexpected happens in the system, such as a large current spike, we want the user to know that. So that is why we developed a notification system. Currently, the user can select which metric they would like to receive pop-up and email notifications for with SMS planned for the future. The reason we implemented these different notification functionalities is to implement diversity in the whole system to ensure the user is notified in case one way, such as email, is not functioning at that time.
As of now, we have a fully functional PDU that can be controlled by a web application. Despite making a great deal of progress, we still have a task ahead of us. To meet our best anticipated outcome, we need the following: a ruggedized case. We need to design a case for our board that meets military standards. Error logging. We need to log errors such as server crashes, as well as enabling users to see those logs. Fault tolerance. We need to make sure any errors that occur will have minimal effect on the end user. Notifications. We need to implement SMS functionality as well as notifications for system errors. Security. We need to implement and test the security of our system for things such as input validation and user authentication. Documentation. We need a full documentation package to aid Acumentrics in future development. And finally, our PDU should be able to communicate with Acumentrics UPS to allow prioritization of outlets in the event of a change to battery power. Now I would like to thank our technical directors, Brendan Smirbeck and Peter Upchek. Without their insight and guidance, we would not have accomplished as much as we did. And of course, Dr. Sunak for giving us the opportunity to take on this project and allowing us to find what we truly are passionate about. Thank you.
So we are ahead of the schedule, and there's a couple of questions. Team will take it now, apart from being at the poster section.
What language did you write your web server in?
The front end,
Yeah.
JavaScript,
Oh.
HTML, CSS.
And what's the time resolution of your voltage and current measurements?
The front end updates every 5 seconds, but the actual sensors run at 0.01 seconds.
Yeah, Frank.
There's a lot of computation and analysis and sensing of levels on here and everything, but one of the big factors here is with the power. Did you learn how to handle the power during your exercise? exercise here, or was that mostly from the classroom?
Well, there's a lot of research in developing the current sensing and monitoring. So for each one of them, or for our official design prototype, what we did was we stabilized each current sensor, each Hall effect we have running right after the relay module, and it's running through the current sensor. So each outlet, as you plug it in, you'll see the spike in current. So that's how we performed the relative power draw from each outlet.
Okay,
And
thank
if
you
you
very
come
much,
back-
Steve.